More Turing machines. You know, we're going to talk about Turing machines the rest of the semester, but I just wanted to do one more example of this business about Turing machines which mark off the letters on the tape as they go. I want a Turing machine for, last time we did one for X followed by X reverse. I want to do one like this, XCX, where X is in AB star. So it is a big string of A's and B's with a C in the middle, and then the same thing from the beginning again. All right, this actually is not context-free language. Context-free language cannot do X followed by X very well. But anyway, XCX is what I want. This is another one which involves some kind of two branches of the path, because the idea is you start with the first letter of X, which is either A or B, and you mark that off, and then you go down until you pass the C, and whatever the next letter is, you mark that off, but it has to match the first letter that you saw. So it's, if the first letter was an A, you want to see an A there. If the first letter was a B, you want to see the B there. So that's the two branching paths. And then you go back to the beginning. Let's just see if we can do it. I hope you all remember how to do these. By the way, we do have homework due tomorrow night. Something weird is going on with the website. I'm not sure what, and I'm looking into it. It's not my fault, but I asked the IT people. Anyway, I emailed the homework to everybody, so that's where you can see it. Yeah, let's see if we can do this. XCX. So I'm going to begin in some state, and I'm going to do these, like I said, two branching paths depending on whether the first letter of the X was an A or a B. In either case, you want to mark it. So I'm going to go A bar, R, and then B bar, R. So you change the A to an A bar to mark it off. And then I want to move to the right. And I want, yeah?
Does it matter how you mark it? Like in general?
How else would you like to mark it?
I don't know, like, I guess what I was thinking of was like, when we were doing the ones where we changed it to like a letter.
Yeah, so we did some examples where we changed the A to an X to mark it. That is usually a bad idea. And actually, ask your friends who actually came to class last week. We talked about that last week.
Okay.
So watch the old videos or look at the old notes. I did some examples marking the A by changing it to an X, which was actually wrong. So be sure to check those out. I believe actually in this example you can get away with changing them to X's, I think, but it's to be safe. It's better in general to mark them by turn an A into an A bar or something like that. Okay, after doing marking the original A, anybody want to suggest what should we do in the next state? Yes?
Should you just like go until you see the C?
Yeah, let's move to the right until we see the C, and then we'll have to start doing something differently. So move to the right. How would we indicate that? I see lots of people doing this. Yeah, make a little loop like that. And you have to write down specifically what are the letters that we expect to move past. I think they would be other A's and B's, right? We're not actually going to go past any A bars or B bars at this point. So I'm going to go AAR, BBR. We move to the right through some A's and also some B's. And after doing that a bunch of times, we get to a C. And I guess we should leave the C like it is. You don't want to change the C to a C bar. So I'm going to say CCR like that. All right. What should we do at this point? So now I suppose we are now pointed at the first letter of X. Yeah? Change the A. Yeah, if it's an A, I would like to mark it off. And then actually this is the point at which we can rejoin the other branch, because now and I'm going to put an L because our next basic trajectory is to go back to the beginning of the string. All right. Actually, I want to add something else to this state. Anybody have an idea? In the first time through the iteration, you don't need anything else here, but in deeper steps, yeah?
You need A bars and B bars?
Yeah, at this point, after we pass the C, we are also going to have to pass some previously marked A's and B's at this point in the string. So I'm going to do one of these with A bar R, and B bar R, like that. Those are the other ones which had already been marked. But eventually you'll get to an unmarked one, and in this branch, it better be an A, in which case you change it to A bar. All right, and now I want to move back to the left. First of all, we're going to go back to the left through some other barred things, eventually arriving at the C. So there's a few different ways you could write this, but I'm going to go A bar L, B bar L. And then go back to the beginning, but with an intermediate step here. At some point we cross a C, and then after the C we want to be moving through unmarked things. That would be the right hand end of this X would be all unmarked so far. So I'm going to do this, A L, B L. Sorry, it's a little crowded in there. And finally, when you get to either A bar or a B bar, that means you made it all the way back to the beginning. And you can start off marking again, like that. We cross over the C, and then we move to the left through any unmarked letters. Once you hit a marked letter, though, leave it like it is, and then you're back to the beginning where I'm pointed at the first unmarked letter again. And I'm either going to go across the top or down the bottom. I guess we can write down. So the steps on the bottom will be the same as the steps on top. The difference would be only this arrow here and this label. Instead of marking an A, I would mark a B. So this, you still need all those other things though. AAR, BBR, CCR, like that. A bar R, B bar R. Like that. I think that is the main loop. All right. So after doing all of this business, we will have marked off every letter. I think now we need some. How do you decide when you're done at this point? You got to think about when you actually finish, sort of where will you end up in this big loop. I would say your last marking will be either one of these arrows will be the last one that you mark. Would be something like if you have, say your string was this. Eventually, at the end it'll look like this. Everything is marked off. And the last one that actually gets marked is there, right? And so from there, and I suppose in this particular example, it would have been here because the last thing I marked was a B. And then it'll do this, back it up through A bars and B bars, getting to C, back it up again, until you see a A bar. That will actually happen right here, and then it will move back. It'll be in this state, pointed at the C. I think that's your clue that you're done, right? If you're in this state and you see, and it's pointing at C, that means you've marked off all the letters at the beginning. Yeah?
So in that middle there, the reason you have the B bar, and A bar,
Yes?
going to the right,
Yeah?
is it because like when you're going all the way to the left, and then you're going to be on a bar?
Yeah, it's because this leftward motion sort of overshoots by one.
Okay.
Somewhere in the middle here, it might look like A bar, A, B, C, A bar, A, B. Like that is what an intermediate step would look like. It passes the C, then I do these go left through the B, through the A, and I'm pointing here.
Okay.
And then I do this arrow and I'm pointing, I move to the right
Oh,
once more.
okay.
It's because that leftward motion overshoots and then you have to move to the right once. So anyway, the signal that you're done is in this state. If you see C in the middle, then that means you have finished marking off the first part. The first part has been all marked. Can I just make this arrow to an accepting state, or do we need to do any extra checking? Yes?
Yeah, you need to go all the way back to the end to make sure you haven't left out any at the end.
Yes.
Through like all A bars and B bars until you hit a blank.
Right. So far we've verified that everything at the beginning before the C has been barred, but we don't know actually there might be extra leftover letters on the end. So we need to run through the whole thing to the right until we hit a blank, verifying that everything is a bar. So it'll look something like that with A bar, R, B bar, R. And then finally, if I see blank after all that, then we can accept. All right, that last bit there is to make sure the rest of the string is actually all bars. And if it is, and you get a blank, then you can accept. All right, if there were extra letters here, extra things that didn't match anything the first time around, then you would just get stuck in this loop, and then the machine would reject. Yes?
So how could you end up with letters that are letters that are unmarked?
Unbarred would be if your string actually is not accepted by this. Like if your string doesn't actually have that format. For instance, if your string was like A, B, C, A. Well, really more appropriate would be something like this. Yeah, too many A's. Sorry. A, B, C, A. The procedure that we've done so far would mark this A, then mark this A, then this A, then this B, then this B, then you see C, which means you're done. But we would have still had these two extra letters. Like this string should be rejected. It would end up looking like that. And those two extra A's at the end are what should make it rejected. And that's why this right here has only bars in it, so that it will actually get stuck if you see extra A's at the end.
So if you didn't do that end step, then it would accept that one.
Then this would be accepted, yeah, but we don't want it to be accepted. Yep. All right, I got one for you to try, which involves this kind of branching pathways, although this one is, it requires fewer states than the one that I just did. Let's do a Turing machine for this set X in AB star, which X has the same number of A's and B's. So my strategy would be, yeah?
Sorry, I had a question on the previous one.
Yes.
Would there be, like, what if there was no, since it's AB star, what if there were no AB? Should there be an acceptance of just C?
Yes, just C should be accepted. But I think actually it happens the way as is. Just C would be accepted because you would start here, you see C immediately go down here. Since I moved to the right, the next letter would be blank and it would be accepted. So yeah, that is something that's worth thinking about. I think you kind of get lucky in this case because it just works the way you want it to immediately. All right, try this one. Same number of A's and B's. My strategy is you look at the first letter, right? And if the first letter is an A, then you have to look through the rest of the string and look for a B and match them together. So you mark off the A and mark off the B. And then you go back to the beginning and see what the next letter is. You need the two branching paths because the first letter might have been a B, in which case you look for another A to match up with it. See what you think. I'll give you a few moments. I was able to do this one in fewer states than the previous one. Yeah, and I think actually these students come out because after that comes Alright. Yeah. So I just went home the next day. See what I did. Do I make a suggestion? I think good. These two guys.
That was like,
Yes, after this point, now,
like negative the Tuesday before.
you match it up. So that's positive.
We were both connected. And then, I got a task eight, and we, I gotta go back, which is a call, and I have to bring up. So I watched it for 40 minutes. So with the D, we go left, if we're going left, we're gonna hit, we wanna hit the first compartment, go no, I think you're going to hit, in this case, A was first, so you're gonna hit the marked A again, right?
Yeah.
So then you're gonna go right, so we're gonna wanna move left.
Yeah.
So we're gonna do that.
I think you said you marked the A, so we're looking at left, right? Looking for a B. Yes.
So we're going to go for the first station.
Well, we could hit A mark here.
So you would say actually,
No,
if you see
because
other
it
A's,
was-
just stay as A, but if you see the B.
Oh my gosh.
Yeah, you can go.
Right.
Yeah, that's good. Okay.
Yeah, that's it. I was gonna do a different state, but I think that's what I was saying.
You have to perhaps go to the bars and use it.
Yeah, we have to loop to the beat actually, because imagine it starts with the beat, so you don't have to break. But what would we do this
Okay.
beat before the end?
There's gonna be another task.
That's pretty good. I think actually one comment that.
It'll loop back around in that
Yes,
sense.
maybe they can come back together. Because if you only need to keep them separate, someone is like actually do this.
It's gonna be the same thing.
It's the same in the opposite.
I think in this example you have to go all the way back to.
No, we're looking.
No, we're looking for an
Looks like folks are doing great. I'm gonna.
Oh, yes.
Oh, I never.
We have AA. Because we're looking for normal.
And then this is
Want to talk about these? I see people, some people have finished, some people are getting there. Let's discuss. I wrote sort of half, I didn't write everything yet, but from the first state, you're looking at A's and A bar, or if you see an A, you mark it. If you see a B, you mark it, and these are my two parallel tracks. If you had marked an A at the beginning, I have to move to the right basically until I see a little b. And so that means you may have to move through other unmarked A's or through marked A's or through marked B's. But eventually you will find a B, hopefully, I mean if the language is actually accepted. And then you mark it. And at this point, the two branches can come back together because I have handled the reason they are branched in the first place is because the first thing may be A or a B. But after you do this step, it doesn't matter anymore what the thing was because I matched them up. Anyway, in this state, I need a loop which moves back to the left. And the way that my strategy works here, you have to actually go all the way back to the beginning of the string until you hit a blank. So I'm going to go left through everything. A, L, A bar, L, B, L, B bar, L. And then eventually we get to a blank, and that's when we go back to the beginning. BBR. Yes?
Why do you want to go back until you hit a blank rather than a mark?
I think that it's possible you have to go even further to the left past a previously marked letter. For example, if the string was, this is a little tricky, but if the string was this, then the steps would be first that A gets marked, and then the first B will get marked. And now, sorry, this is not, yeah, I wanted another, what was the question? Why do we have to go through marks here?
Why do you have to go all the way to a blank versus going back to the first mark?
Going back to the first mark. AAB, oops. I think you really do have to go all the way back to the beginning.
Maybe because you don't know which is the first mark. Like, isn't there not a way to tell really until you hit a blank?
Yeah, because you might see a mark with a another letter still to the left of it that you need to find.
But if you took two separate paths,
If you,
you would look to the first mark A, but if you did B, you look to the first mark B. You couldn't do it like that.
I think the issue is that the first marked letter that you see, there may be unmarked ones to the left of it. I think that that's possible. Although, sorry, I'm having a hard time coming up with a specific example when that would happen. Yeah, maybe it's not. Then this one gets marked. Something like this, I don't know. You would end up marking this one and also this one. Yeah, then the next, so you would mark those two, then the next time through, it ends up with B bar, the next B gets marked, and this B gets, no, and this A gets marked. And then from here, as I move to the left, if I stop at this marked A, I will have missed that B, and I'll just go to this B. So.
But since you marked an A, we would look for the next marked B instead. Like we didn't join the paths in the center.
That might do it.
Okay.
Although I think what I'm doing is easier.
Okay.
But that may address the situation appropriately. There are, of course, many ways that you can do this. And you don't have to feel like you have to get the same answer that I do. Yeah, sorry, I'm a little slow on the thinking of the examples. Anyway, this is mostly it. Anybody feel like I need to add some stuff? There is some stuff, yeah.
A loop for B bars and A bars to the right. So you hit a blank.
Yes. You mean on the starting state? Yeah, right. If you do go all the way to the left, then before you make your next mark, you're going to have to move to the right through some previously marked letters. Excellent. And I think there's one other major ingredient that I need here. Yeah, an accepting state somewhere. Where should that be? And do I need an extra, sometimes we need an extra, like, check some extra stuff. I think you don't in this case. But, so how should I do it?
From the starting state, we can check if there's a blank.
Yeah, right. I think this will do it. In the starting state, if we see a blank, this will happen if everything was marked off. You will do this loop and go all the way across the whole string. Yeah, and you don't have to run through the whole thing an extra time just because this side already would have run through the whole string going to the left, and now you run through it again going to the right. That will make sure that you actually covered everything. All right, excellent. Thank you for doing those. This is a tricky business a little bit. You have to think very carefully about your strategy as you go letter by letter, but it sounds like folks are getting it. I hope you are getting it, because I'm giving it to you. All right, let's move on to something a little different. So this is basically it for sort of I tell you a language and you write a Turing machine to do that particular language. You'll see some more of those on the homework, of course. I would like to talk for a bit about what we call Turing computable functions. This is something still about Turing machines, but really from a different point of view, you might say. So Turing machines, as we've been discussing them so far, Turing machines either accept or reject strings. Right? But a Turing machine, we can also think of like a computer in the sense of a computer. How we usually think of a computing machine is I give it some input and it tells me an answer. It doesn't just say yes or no every time. Like a calculator, you can type a number, you can type some stuff into it, and it tells you some other stuff is the answer. All right. So Turing machines either accept or reject strings, but it's maybe a little more, that from an abstract point of view, that's what a Turing machine does, but maybe a little more applicable or a little more similar to what we usually think of as computers is a machine which actually gives an answer, like a sophisticated answer, other than just accept or reject. So, but I'm going to say we can use a Turing machine to compute a function and return an answer. This is what people generally think of when they think of computing devices. They are things which give you an answer when you give some input. All right. So in this way, we are going to think of the Turing machine as a computer which is computing the answer to some function. The Turing machine starts with input on the tape, and in this way of using a Turing machine, rather than just accepting or rejecting, and it halts, that is to say, it stops after a while with the answer on the tape. All right. This is the idea. The Turing machine starts with some input on the tape, and it halts with the answer on the tape. In all the examples we've done so far, we don't really care what the tape looks like at the end. It doesn't matter if the input has been all marked up or maybe it's been blanked out or something. None of that really matters for a Turing machine, which is just about accepting or rejecting. But for a Turing machine, which is about computing functions, the machine still has all the same properties to it, but we can use it in this other way, where it starts with some input on the tape and it finishes with the answer for whatever function it is you're trying to compute. So here's a simple example. And I'm going to give a name to this machine. I'll call it M. And let's say that this is M. It has a... I didn't mean that. Sorry. It has an arrow here. A, L, B, B, L. And it has an arrow here. Blank, A, R. All right. It doesn't have an accepting state because this Turing machine is not about accepting or rejecting. It's about doing something, right? It starts with a particular input on the tape, and when it's done, the tape looks different, and that's the answer. So I would like to think about, what does this machine do? It starts with a particular string, and it ends with something. Can anyone describe, like in words, what happens when you start with a particular string on the tape? What does it end up looking like? Like, we could do a specific example. If we start with, let's say, BBA, it will end with, can anyone say what will the tape say after it does its thing and eventually stops? Yeah?
Will it just be BB and then a bunch of A's?
I don't think so. So we begin with BBA on the tape, and the head will be looking at the first B, right?
So will it be ABA?
It will be A, say that again?
ABA or ABBA?
I believe she said ABBA, yeah. It starts off by looking at the first B. You see this first arrow? The machine leaves what it is, but moves to the left by one position. And then this arrow takes a blank and turns it into an A. So this thing begins with BBA. The machine moves left once and then changes this blank into an A. And so the result is ABBA. We can say M. We say M computes the function f of x equals ax. All right? The function, what it does is, just explain in simple words, what it does is it puts an A at the beginning of the string, right? Because it moves left by one position, and where there was a blank, it writes an A into that spot. Another way of saying that, sort of a fancier way of saying that, is like this. Puts A at the beginning of the string is like this function, right? F of x, where x is a string, the answer is ax. Puts an A at the beginning of the string. So this is, we say M computes this function. And the big question that I want to talk about is, just like you can ask about what kinds of languages can you accept or reject using a Turing machine, when you formulate it in this way, you can ask about which functions can be computed by a Turing machine. Like, apparently that function, which is a very simple function, can be computed by a Turing machine. But the large question is, which functions can be computed by a Turing machine? All right, that's the big question. It is on some level equivalent to asking what are the languages which can be accepted, but it's because it's the same machine we're using, but it's a different way of phrasing the question, really. All right. Which functions can be computed by a Turing machine? Here's another example. How about, can we make a Turing machine for this function, f of x equals xb? That means whatever the input string is, it puts a b on the end of it. Can you do that with a Turing machine? I think you can. You want to think about what would your strategy be for that? To put a B on the end of the string. Anybody got an idea? You could just say in words, yeah.
Go to the end, and if you see a blank.
Yeah, right. Move all the way to the right until you see a blank, and when you do see a blank, change it to a B, and then stop. So that would look like, go all the way to the right, looks like this, AAR, BBR, and then when you see a blank, you change it to a B, and I suppose you could go another, move to the right again, I guess. That last R there doesn't really matter, but. I changed the blank on the end to a B. There it is. So this is a Turing machine for that function, f of x equals xb. How about this? Can we make a Turing machine? You guys can try. Make a Turing machine for f of x equals axb. How about that? This is kind of a combination of those two machines. Although I wouldn't necessarily suggest you think of it in that way, but you want to put an A on the left side and a B on the right side. See what you think. Yes. No. Yeah, there is no accepting state, so you just make it so that the machine gets stuck. I mean, usually there will be sort of a state like this where nothing else happens after that.
Why can't you just accept it?
If you want. I mean, yeah. You want to put him out a circle? That's fine. It doesn't really matter. I think it's typically not done that way just to emphasize the fact that this Turing machine, its job is not to accept or reject. Its job is to do something else. I see some folks came up with something. My strategy would be move to the left once and then put the A where a blank used to be, and then go all the way to the right and put a B where a blank used to be. So I would say AAL, BBL. This moves you to the left by one spot. Then put a little A where that blank used to be. Then move all the way to the right, AAR, BBR, and put a B where a blank used to be. All right, that's how I would do it. If you want, you can accept. How about 3 circles? How do you like that? That's silly. All right, this is how I would do it. F of x equals axb. So here's a little definition. A function like this, which you can do using a Turing machine, is called Turing computable. That's why I said this whole section is about Turing computable functions. So I'm going to write that as an official definition. If, let's say, f is a function, typically we would say the domain and the codomain. I'm going to do, this is something slightly subtle here, but f is a function from some set of strings to just sigma star, which would be any string on the letters of the alphabet. If this is some function for some domain S, which is a subset of sigma star. So all I'm saying by this is that the domain does not have to be all possible strings. It could be a function which only uses certain types of strings and gives you some answers. The codomain, the answer could be any string, but the domain sometimes, in some examples, we want to have some kind of restricted domain. But anyway, if this is some function on some domain, it's kind of the same reason that sometimes we want to write something like f of x equals 1 over x. This has a different domain than all real numbers. Its domain is all real numbers except for 0. The domain of the function might not be all possible strings, but it could be. But the answer certainly could be any string. Anyway, if this is some function for some domain, we say that f is Turing computable when there is some Turing machine I'll call it M, such that when we start M with X on the tape, it halts with f of x on the tape. Right? You run your machine with starting with the input string on the tape, and then the machine stops with the answer f of x on the tape. If that's possible, then f is called a Turing computable function. It means it is possible to get the answers using a Turing machine. All right. The examples that we've done so far have been fairly simple. Here's another example with just showing how sometimes that kind of restricted domain comes up. How about a function where f, we start with some string like b to the n, a, b to the n, and the answer is b to the n, a squared, b to the n. So this is one in which the input always looks like a bunch of b's with one a in the middle, and then the same number of b's. That's what the input always has, that format. And then the answer is supposed to be, I just squeeze another a in the middle there, right? So here, this is an example where the domain is not all possible strings. The domain is s equals the set b to the n, a, b to the n, right? This function only takes strings of that format as the input. That's fine. All right. Any ideas about your strategy for this one? I said it out loud. All you got to do is this A, you just like squeeze another A in the middle there. Although when you think about the mechanics of how the tape is supposed to work, there is no like squeeze another A operation that you can do on the tape. So you got to be a little fancier than that. Anyone want to suggest a strategy? Of course, you begin looking at the front of this string. Change the B, so change this first B to a A, yeah, and then?
At the end, change the blank to the B.
And then add an extra B on the end. That's what you have to do here. This is not really hard, although you have to think about exactly what the strategy is. So the idea is you start with B to the N, A, B to the N, and my strategy is change the first B on that part, not the very first B, but the first B here, to A, and then add a B on the end to compensate for that one. All right. Okay, let's see. Can we make that happen? We need to begin by first moving through all the B's at the beginning. So that can just be one of these, B, B, R, and then once you see an A, leave the first A like it is. Change the next B to a A. So this would be like that, B, A, R. And then go all the way to the end and add an extra B. So go all the way to the end is one of these loop things. A, R, B, B, R. And add an extra B is blank B, R. I think that'll do it. Yes?
Wouldn't you need to check that there's the same amount of B's in both sides?
This is a good idea. Is it necessary to check that there's the same number of B's before and after? I think it is not necessary in this case because the domain is this. That means the string you're given is already guaranteed to have this format. B to the n followed by A followed by B to the n again. So it's not our job to verify that the input is valid. That's I mean, you could additionally do that, but that's not what we're trying to do here. All right, great. We got 3 more minutes. I had another example to do, but maybe we'll just start off next time with that. The big question to ask, though, is what kinds of functions are Turing computable? All right, see you next time.